in the quadratic formula, we're going to get x equals -1 plus or minus the square root, 1 minus 4 times -8, so it's plus 4 times 8 over 2. Now, in order for us to be able to graph this, I have to put it in the calculator and get the points, right? So it'll either be, on a, like on the homework, let's say, right? You put it in and you get that x is equal to, what is it? I have it here. -3.37 and 2.37. Huh? Well, you have to in order to be able to graph it. So now, -3.37 is right here. And then 2.37 is right here. So this asymptote, I knew it wasn't slanted properly. So it's more like this. Okay, so positive 2.37 is right there. So now, on the left-hand side, we know it's going to follow the red vertical asymptote there and the oblique asymptote here. And it's got to cross the x-axis at that green point. So really, there is one way for it to look, and it's this. Okay? Dylan, I think people are looking for you. Okay. So if the graph went off the screen on the top over there, it has to re-enter on the opposite side. So it re-enters here. It's got to cross the 0 and follow the blue asymptote so it looks like that. Okay? I have to say, with these, things can get a little bit trickier. When I give you these on the test with the oblique asymptote to graph, they will be pretty straightforward. I can, however, give you any old problem, tricky or not, and ask you, all the beginning parts except for the graph. You know what I mean? So I do, pick like the good ones for the tests and quizzes and stuff. Okay? Questions? Okay. So we've been talking about, the terms in the denominator that can cancel, right? So if in the denominator of the rational function there is a term that can cancel, those terms will give us removable asymptotes or holes in the graph. Okay? So take a look at this one here. When I factor, I get x minus 3, x plus 3, x minus 3, x plus 2. Now, before I start canceling things out like crazy, what's the domain? It can't be 3 or -2, right? Those are both discontinuities. So it's -infinity to -2, -2 to 3, 3 to infinity.
So you do the domain before you cross.
I do, because then I don't want, to falsely eliminate things. Now, these things will go away. So my vertical asymptote is just x equals -2. Okay? Huh? Because the 3 will give us a removable discontinuity. Right. Yeah. So now there is a removable discontinuity at x equals 3. So at x equals -2, I have the vertical asymptote. At x equals 3, somewhere here, there is a removable discontinuity or a hole. And then Okay, for the horizontal asymptote, I do like to go back to the original function, and it's y equals 1. Now, when all is said and done, this function up there reduces to x plus 3 over x plus 2. Okay? Okay, so now, let's figure out what the zeros are. So let me put in the horizontal asymptote. Okay, so what are the zeros? Yeah, you set the new numerator, right, equal to 0. X equals -3. So there's the 0. Okay? Now, somewhere on this vertical line of x equals 3, there is a removable discontinuity. Where is it? How do we find it? Well, the way you find it is you can plug x equals 3. You can plug, x equals 3 into this function. However, you have to be careful here with the notation, because technically at x equals 3, does the graph exist? No. So there is no y value at x equals 3. There is no f of 3. It's undefined for f of 3. The way we go around it is we can use a limit. So that's the notation that we can use. So I can say the limit of f of x as x approaches 3 is 3 plus 3 over 3 plus 2, 6 over 5. That is the vertical location of that removable discontinuity. Okay? So this is the vertical location of removable discontinuity. So at x equals 3 and 6 over 5, there is that removable discontinuity. Okay? So here's another question for you. What if at some point I asked you for the y-intercept? How would you find it? Plug in 0, right? That's f of 0, and that'll be 3 over 2. F of 0, 3 over 2. So I'm just going to, put that in there. Why? Because what if you're asked one day? Okay, so now look at what my graph is going to look like. On the right-hand side, it's going to come down and look like this. And on the left-hand side, it's going to come up from here, cross the x-axis there, and follow the asymptote there. Okay? All right. How to solve functions, rational functions. We've done this, you've done this before. Basically, to solve a rational function, you have to multiply each term by the LCD of the function, right? So here I have x over 1, x minus 6. The LCD is x minus 6. So I multiply everything by x minus 6. So here I get x times x minus 6 minus 4 equal to 0. Huh? You multiply every single term by the LCD. Even, not the denominator, but like the x, the 4 over x minus 6, and the 0. Yeah. So here I get, okay, so here I'm going to distribute. But before I do that, let's do this part. Are there any restrictions? Restrictions are what x can never equal for this function, for this 6. So you say restriction X cannot equal 6. Okay? All right, let's continue solving this guy. X squared minus 6x minus 4 is equal to 0. So x, here we can't factor. So x is equal to 6 plus or minus the square root of 36 minus 4 times a times negative 4 all over 2. So x is 6 plus or minus root 52 all over 2. And so that is 6 plus or minus 2 root 13 all over 2. And how much is that? Yup. And since none of those is 6, those are both good enough. Okay?
Is the restriction also x can equal 0?
No, just 6. Whatever makes the denominator 0.
Can you go for 1? Oh, so you have to go back to the original?
Yeah. 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 So look at this one. First, I'm going to factor this, and it's going to be x minus 6, x plus 3. Okay? Now, what are the restrictions? Let's do that first. X cannot equal what? 6 and negative 3. Okay, we're going to multiply everything by the LCD, which is x minus 6, x plus 3. X minus 6, x plus 3. X minus 6, x plus 3. Yeah, I mean, yeah, eventually that's what's going to happen. If you can do it that way from the beginning, that's fine. So x minus 6's go away and everything cancels there. So what you have now is 2x, x minus 6, plus 3, x plus 3, equal to 27. So, distribute, distribute, distribute. 2x squared minus 12x plus 3x plus 9 equals 27. 2x squared minus 9x. And then if I subtract the 27, I get minus 18 equal to 0. This is factorable. And in fact, you get 2x plus 3 and x minus 6. Huh? So from here, we get x equals negative 3 over 2. From here, we get x equals 6. But that doesn't work, so you throw it away. So x is just negative 3 over 2. They can all work. One can work. None can work. It's all okay. Okay? Cool. So, take a look at this one. This is the lens equation. So, in your eye, for example, so when you have an object, like the light hits the object, right? Like from here, and then the light goes into your eye, passes the lens, and then focuses behind the lens, and then there is an image printed in the back of your eye. Interestingly, that image is upside down, and your brain switches it to right side up, okay? So, you don't have to know much about that. The way these the way these things are related to each other is this. The distance between the lens and the object is DO, distance of the object. The distance between the lens and the image is DI. The F is the focal length. This is where, like, when all the light rays come in, where they converge. You don't really have to know much about it. But basically, they're related in this formula. Okay? So, this is the lens equation. And here, if you go to the second line, it says, suppose the image is 10 centimeters from the lens. So that tells you DI is 10. The focal length is 6. That tells me F is 6. Then it asks me to write a rational equation to model the situation. And when it says rational, it doesn't mean like something that makes sense, right? Rational just means like something over something. So the equation is 1 over F equals 1 over DI plus 1 over DO. What is F? 6. So 1 over 6 equals to 1 over 10 plus 1 over DO. That's it. Just writing an equation. That's it. Then it says to solve, to find the distance from the lens to the object, that's DO. So, if I have my cute little equation, what is the common denominator? What's the LCD here?
60.
Or there's a smaller, 30DO. 30DO. It looks kind of weird. Okay. So now, here I get 5DO equal to 3DO plus 30. It's kind of unfortunate with all the 3's and the circles and the O's. Okay? So, 2DO is 30. So then how much is DO? 15 what? Centimeters. Okay? Yay. For this homework, circle the green, not the green ones, the red ones. That's what you're going to do. Question, yes.
In this case, if we just like subtract 1/10 from 1/6, it's kind of the same way with LCN, but it's just like
Yeah. It's the same. It's the same. Yeah. Okay. Okay. So let's move on. All right. Yes. Okay, let's move on. Oh, we have like 35 minutes left. 25 minutes left. Sorry. Yes. Are you sure?
Yeah, I'm good.
Okay. We're going to talk about Tuesday. Nonlinear inequalities. Nonlinear inequalities. Yes, they are. So, we can write a polynomial equation, blah, 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 equals 0, and then solve it. And there is like one solution. Or I can write it as, the function is less than 0, greater than 0, less than or equal to, and so on. What do these mean? Here, this means f of x is negative. That means f of x is below the x-axis. And if I say f of x is greater than 0, where is the function? Above the x-axis. So take a look at this cute little f of x here. if you see this first portion, oh, so first let's talk about where the zeros are. You have 1, 2, 3, 4 zeros. The portion here is above the x-axis, right? The portion here is above the x-axis. These are the regions where f of x is greater than 0. These regions are where f of x is less than 0. So, if I ask you, where is f of x greater than 0? You would tell me the intervals, like the increase, decrease, you would tell me the intervals. So look, if I say where is it greater than 0, you would say, okay, this interval from negative infinity to, what is this? 1, 2, 3, negative 4. And then from negative 2 to 2. Now, if I asked you, where is f of x greater than or equal to 0, that will be negative infinity to 4, including 4, and negative 2 to 2, closed brackets. Do you see the difference? Huh? Negative 4. So the one case is open parentheses, the other case is closed brackets. Okay? Now, notice one other thing. Here, at x equals negative 2, what is the multiplicity, would you say?
41.
Odd, right? It's an odd multiplicity. When it's an odd multiplicity, the graph switches between negative and positive. So here the graph is negative, here the graph is positive. What about at x equals 4? It's an even multiplicity, and when it's an even multiplicity, the graph does not change sign. If it's negative, it stays negative. If it's positive, it stays positive. Okay? So, f of x changes sign at odd multiplicities. Okay, so how do we solve one of these inequalities then? The process is simple. We have to solve f of x as if it was an equal sign. But then we have to create a sign chart. Okay? Plot the zeros on a number line, and then we have to test values. Okay, let's do one, guys. So first I have to move everything to the same side. X squared minus 8x plus 15 less than or equal to 0. Factor x minus 3, x minus 5 less than or equal to 0. What are the zeros here? X equals 3 and 5. Okay, I'm going to put those on a number line. Oh no. Okay, now what I'm going to do is plug in test points. Yes, this is the sign chart. Now I have to plug in test points from each region. So, from the leftmost region, let's plug in 0. Okay, where to plug it in? You have to plug it into the one where it says less than or equal to or whatever 0. To the one where it's comparing to 0. Now, whether you plug it into the top or the bottom is up to you. I like to plug numbers into the factored form because it's easier for me. I do realize with the 0, the top one is easier, but you know what? We're going to make things so much simpler right now, it doesn't really matter anyway. So, if I plug 0 into here, In the first parenthesis, I get a negative number, right? 0 minus 3 is negative. In the second parenthesis, I get another negative. That makes positive. Positive. From the next interval, I'm going to choose 4. 4 into the first parenthesis is a positive number. Second parenthesis, 4 minus 5 is a negative number. That makes negative. Next, I'm going to choose 6. What do I get for 6? Positive, positive, positive. Now, my equation is asking for less than or equal to 0, the negative regions. That's this. So I say the function is negative from 3 to 5, or from 3 to 5, like this. Closed brackets because it's less than or equal to. That's the answer, 3 to 5. You just want the region. Okay? You just want the region where it's negative. This is telling you your function has to be negative. Where is it negative? Here it's negative. Yeah.
If it was the two outside, would you do the union?
Yeah, we're going to do so many examples and you'll see. Now, let me show you something here. Where did we get this 3 from? X minus 3. Is multiplicity odd or even there?
Odd.
Odd. At odd multiplicities, the graph changes sign. So, on one side of 3, it's positive. On the other, it's negative. Where did we get 5 from? Here. Odd. On one side of 5, it's negative. On the other, it's positive. So, from now on, that's what we're going to use. I just choose one number to plug in, and then I just like boom, 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 do the sign. I'll show you. Okay. Let's do this one. All right, move everything to the left side. X cubed minus 3x squared minus 22x plus 24 greater than 0. Okay? This is a cubic function. We have to do P over Q. Let's do P over Q. So, we can you factor by grouping? How?
3. So it doesn't equal to.
We could have totally done it by now. Okay? Let's just go in order. Let's try number 1. Let's try 1. 1, negative 3, negative 22, positive 24. 1 comes down. 1. Negative 3, negative 3. No, sorry, negative 2. Negative 2. Negative 24. Negative 24. 0. So, I know. So, x minus 1, and then x squared, minus 2x, minus 24, greater than 0. Can we factor that?
Yeah. X plus 4.
X minus 6, x plus 4, greater than 0. Okay, so what are the zeros that go on the number line? Negative 4, 1, 6. Okay, this time I'm only going to choose to plug in one number. And my favorite number to plug in is always what? 0. So let's do 0. I'm going to plug 0 into these parentheses. Here, I get negative. Second parenthesis, I get negative. Third parenthesis, I get positive. Together, that's positive. Negative, negative, positive. Yep, positive. Now, take a look. Look at negative 4. Where did negative 4 come from? Here. Odd multiplicity means at negative 4, sign switches. So if it's positive to the right, negative to the left. At 1, odd multiplicity, sign switches, negative. Where do we get 6 from? Here. Odd multiplicity, sign switches to positive, we're done. Okay. Now you only have to take the positive ones, yeah.
If that was x plus 4 squared.
Then it would be plus plus. We're going to do something. Yeah, yeah. Okay, so we need the regions where it's positive. So here and here. So we're going to do here negative 4 to 1, parentheses, not brackets. Because it says this is greater than 0. Yeah. Union 6 to infinity. Cool. Okay. Factor the next one. Yeah, just, yeah, yeah, yeah. Factor this one. Can you? You can't. So you do quadratic formula and you get an imaginary number. That means, wait, that means there are no real zeros? Can that be? That can be, of course. So it's a parabola, you know, it doesn't cross the x-axis. That can be. It could be either above or below. So what do we do in this case? We have no real zeros to put on the number line. But you know what? We draw a number line anyway. And to give it some perspective, we put the 0. Now, for this one, I'm still going to plug in some test points. But we have to be systematic about it. It's wise to first plug in a 0. So when I plug 0 into this function, I get a positive number, right? Positive 3. When I get a positive number and plug it in here, positive again. Okay, what if I get a negative number, like negative 3? Squared, it becomes positive 9. Then negative 6. That's a negative, but a smaller negative, and then positive again. So it'll end with positive. So if you think about it, no matter what negative number you put in, first you're going to square it, make it a very large positive. Then 2 times that negative is never going to be enough to overpower it. So this is going to be positive always. That means it looks something like this. So now the question is, where is this function less than 0? No solution. No math involved, really. Okay? Yeah. Then, you know, it would, yeah, different problem. Here, same problem. It's asking where is it greater than or equal to 0? All real numbers. Is it ever equal to 0? No, but this is saying where is it either greater or 0? So one or the other has to work. So this is all real numbers. I do. We should get into calculus notation. Because it's the same function. It's saying where is it greater than or equal to 0? Right? Yeah. Mm-hmm. So this next one, completely different problem. This one we can factor. And the 0 is negative 6. Yeah. So at negative, so at negative 6 it's 0. I'll just put that over there. If I plug a positive number in here, I get positive, right? But look, where did we get negative 6 from? Even multiplicity. So on both sides, it's got the same sign. Positive, positive. Okay, okay. So this is asking you, Where is it less than or equal to 0? Where is it less than 0?
Never.
Never.
It's equal
Where
to
is it
zero.
equal to 0?
-6.
At -6. So the answer is just -6. Either or. This is, set notation, or x equals -6.
Wait, are those parentheses or like?
It's curly brackets.
Is that different than parentheses?
Yes.
Like, I
So
don't know.
sometimes people do this. This is utterly wrong.
Wait, it is?
Yeah. Curly brackets or like that.
Wait, why curly brackets?
It's the set builder notation.
Okay, I've never used that.
It's set.
Wait, why is, oh, so then that's wrong because it's like,
It's not proper notation.
even though we've been doing it like that.
You haven't been doing it like that. We've been doing it like that if it's an interval.
Oh, when it's not an interval, you need that.
It's just like a three times.
Okay. Oh my goodness. Okay. So, what if we have a rational inequality, right? Like something like this, irrational ones. The process is the same with one additional hiccup. And the thing is, until now, we've been seeing that a function can go from positive to negative at the zeros. But if it's a rational function and it has vertical asymptotes, it can also change sign at the vertical asymptotes, right? So you see here, on one side of the vertical asymptote, it's negative, on the other, it's positive. So all that's different is when you do the number line, you also put in the discontinuities, okay? So you also include the zeros of its denominator in the sign chart. So let's do this one. Man, okay, math is awesome. Okay, so let's do this one. What are the zeros here? 3x plus 4 equal to 0. X is -4/3. Now, so on my number line, I'm going to put -4/3. But I also ask myself, because this is a rational function, where are the discontinuities? X equals -2. I also, okay, shh. I also put the -2 there. Now, I'm going to plug my test points into this, okay? So now, let's do a 0. In the numerator, I get 0 plus 4. In the denominator, I get 0 plus 2. I don't care what the values are. All I care about is it's a positive. So, in the region where 0 exists, this is positive. Okay. Where did we get the -4/3? Here. Multiplicity of 1, odd. So here it changes to negative. -2 came from the denominator. Multiplicity of 1 changes to positive. Okay? And there you have it. Now, I want this function to be greater than or equal to 0. So that's this and this. So it's -infinity to -2. Is that right? No. Why not? Right? So open there, even though it's less than or equal to, or greater than or equal to. Union, close that -4/3, infinity. You see all that action there? Right? Okay. Okay. Last but not least. Okay. So, this one, we're going to multiply both sides by the LCD of x minus 2. So I'm going to get x squared minus x minus 11 less than or equal to 3x minus 6. Okay, let's move everything to the other side. X squared minus 4x minus 5 less than or equal to 0. Here, when I factor, I get x minus 5, x plus 1 less than or equal to 0. So on my number line, I'm going to put negative 1 and 5, but also what else? 2 from the denominator, because the denominator initially was x minus 2. Okay, now it's time to plug in the points. You have to plug in points to an inequality that compares it to 0, not to 3, to 0. So first what you have to do is move the 3 over to the other side. So here's the original function. Move the 3 to the left. So minus 2 less than or equal to 0. Okay, so you plug into this. Yes, I don't know why I got my 3's and 2's mixed up. Okay. No, because here, when you plug it into here, the bottom ones, you've gotten rid of the denominator. You've changed the problem, so you're going to get different results. Okay? You have to put it in the beginning before you did anything to it. So now let's plug in a 0. In the numerator, I get 0 minus 11 over 0 minus 2 minus 3. So that's negative 11 over negative 2, which is a positive number, minus 3. That's going to be positive. Right? Because 11 over 2 is like 5 point something, right? So at 0, it's positive. Okay, at negative 1, does it change signs? Yes, because it's an odd multiplicity. At 2, does it change signs? Odd multiplicity, yes. At 5, does it change signs? Yes, it does. We want the negative regions, so here and here. So we have negative infinity to negative 1, closed bracket, union, 2 to 5, closed or open? Open, then closed. Okay? So homework for this is every other odd. Question.
Why are we going to do as 0?
We're not counting 2 as a 0. Remember what we said earlier is when you have rational functions, you also have to put in the discontinuities because it's possible for the sign to change at the asymptotes.
So, like in this one, like, why are we just like assuming that it changes?